Pangea is the most famous supercontinent because it's the one that scientists have been able to date and study the most. But it wasn't the first. And by studying these older, more ancient supercontinents, we can not only learn about Earth's past, but perhaps even better understand how Pangea formed in the first place. Today, let's talk about what came before Pangea, starting with the oldest named supercontinent, Vaalbara. Scientists think that life began in shallow pools on the landmasses which were floating around before Pangea. So if we want to understand where life might have begun, we need to know what those landmasses looked like. So what do we know about them? Well, our best current estimate for when the Earth's land first coalesced into a supercontinent comes from this pile of rocks in Western Australia called the Pilbara Craton. The rocks here are at least 3.6 billion years old. And if they formed part of a larger continent, then that means there was dry land on Earth 3.6 billion years ago. And we know from studying fossils that life started pretty soon after that. But the thing is, we do not actually know if these Australian rocks were part of a larger continent, or if they just assembled themselves into a landmass all by themselves. It's possible that they were part of a larger piece of crust called Vaalbara, which is thought to have formed between 4 and 3 billion years ago. Vaalbara would have contained parts of what today is Western Australia, South Africa, and India. But we do not know exactly where or when all these chunks came together to form a true supercontinent. It could have been all one big chunk, or it could have been a collection of smaller chunks that collided over time. Our understanding of Vaalbara has changed quite a bit over the last few decades, and it may continue to change again in the future. So, while we will probably never know too much about it, it is very likely that Vaalbara was not the first supercontinent. Life as we know it probably would not have existed without it. But let's go even further back, you see. We have lots of evidence that 4 billion years ago, asteroids rained apocalyptically down on Earth, and we have lots of evidence of volcanic activity on Earth during that period as well. We also know that there was no oxygen in the atmosphere yet, and the conditions were very different from what we are used to today. So under these conditions, how did land even form in the first place? Well, according to some scientists, it started out as piles of minerals that were brought up from the mantle via volcanic activity. These piles of igneous rock would have been created by hot magma squeezing its way up through cracks in the crust and then hardening into rock once it reached the surface. Over millions of years, these piles grew bigger and bigger, and they could have acted as seeds for future continental growth. We can tell that this process took place billions of years ago because these kinds of igneous rocks, called greenstone belts, are found all over the world in places which were active volcanically during this time. Some geologists think that instead of the Earth's crust being broken up into separate plates, it was mostly one giant pile of gooey rock. They call this a magma ocean. Underneath the magma ocean was a layer of solid rock called the lithosphere, and above it was a layer of hot but still molten rock. Over time, the heat from below would have melted some of the rock in the middle layer and caused it to bubble up towards the top. Eventually, this bubbling up would create mountains that poked their way above the surface of the magma ocean. Once they were exposed to the air, these mountains would have cooled and hardened, forming the first true igneous rocks. Then, after more volcanic action, those igneous rocks could have become part of larger piles of rock, becoming part of the first protocontinents. We know that the Earth had cooled enough for water to exist as a liquid by 4.4 billion years ago. And since water is so good at transporting things, we can imagine streams and rivers forming on early Earth. Those waterways would have carried small sediments away from the central mountain ranges and deposited them on the surrounding land. Over time, these deposits would have hardened into sedimentary rocks and added to the growing land masses. Eventually, the plates would start moving and colliding. The piles of rock that became the first continents would begin to take shape. There is some evidence that these first continental piles began forming 4.4 billion years ago, like this pile of rocks in Greenland called the Isua supercrustal belt. This pile is made of ancient sedimentary rocks, but it's hard to say if they formed on land or in shallow water. And because these ancient rocks are so worn down and metamorphosed, they aren't much use for radiometric dating. Researchers have estimated the age of the Isu belt to be between 4.3 and 4 billion years old. But there's a lot of debate about whether that's really as old as it seems. If it is that old, though, that would mean that the first continents formed extremely quickly. perhaps within a few 100 million years of Earth's formation. On the other hand, we know that the first continents were not stable for long. Just a few 100 million years later, most of the continents we know today were still just piles of loose sediment on the seafloor. So any continental crust that did form during this period was probably destroyed soon after. So why does any of this matter? Well, we think that life started on Earth soon after the first continents formed. We have evidence of some of the earliest known life forms in the form of microfossils found in 3.5 billion-year-old rocks. And if we want to understand where life might have begun, we need to understand what Earth was like at that time. The thing is, Earth wasn't like it is now. In fact, it was pretty different. And that's because even 3.5 billion years ago, the Earth was still very young. Our planet formed about 4.5 billion years ago, so 3.5 billion years ago, it was still about 1 billion years from reaching its current size. So the Earth kept growing even as life on it was getting started. Not only that, but the sun was also much dimmer when the Earth formed than it is now. That meant that for the first few billion years of its existence, the Earth was a much colder place. Since the Earth was cold, it didn't have an ocean, until it was about 4.4 billion years old. And since there was no ocean, life couldn't evolve until after the ocean formed. But once the ocean did form, life evolved very quickly. However, the Earth was still bombarded by asteroids during this time. This bombardment heated up the surface of the Earth, boiling parts of the ocean and vaporizing whole lakes. Yet life still managed to evolve and grow. Some scientists think that life got a head start on evolving in places that were protected from the asteroid impacts, such as deep-sea vents. Deep-sea vents are places where hot water mixes with cold water from the ocean. As a result, the temperature varies less with depth near deep-sea vents than it does in normal ocean water. So even if there were fewer asteroids hitting the surface, any life that evolved in near deep-sea vents would have been protected from the worst of them. Because of this protection, life may have gotten a head start on evolving near deep-sea vents, allowing the first life forms to grow larger and live longer than they would have otherwise. So far, we haven't been able to find any direct evidence of the very first life forms on Earth, but maybe someday we will. And if we do, it will be thanks to learning more about the continents and oceans that allowed life to evolve in the first place. Studying the formation of Pangea will help us better understand how life evolved. And by studying the older supercontinents, we can learn about how Pangea formed in the first place.